Hello everyone. From today we are going to begin a new series. A series where we will be solving multiple choice questions on various topics of physics. And to begin with, I have chosen one of the most difficult topics as per the students, which is quantum mechanics. And under quantum mechanics, today I will show you how to solve some of the problems pertaining from the topic Blackbody radiation and Compton effect. Without any time waste, let us jump into our questions. The wavelength at which the radiated energy. Dear students, sometimes you will also see that a language other than radiated energy is also there, something like the wavelength at which the spectral energy density of emitted radiation at temperature T from a black body attains maximum value is proportional to the options which have been given to us is 1 by T, T to the power 2, T to the power 4 and T to the power 3 by 2. Now reminding all of you that whenever you come across a question where energy density or energy attaining maximum value has been mentioned, also the temperature also is mentioned. Remember, we are talking about the Wein's displacement law, which says lambda mt is equal to constant. So very easily we can find out this particular lambda m as the constant divided by the temperature. And if you see, which means that lambda m is proportional to 1 by T, or it is inversely proportional to temperature of the black body. And hence we can readily choose the option A as our correct option. Moving forward, Wein's distribution law holds well for the energy distribution in which region in the black body spectrum? Low frequency, high frequency, low wavelength or all wavelengths? Now just look into this graph. As you all can see that the Wein's distribution law has been shown with the help of the arrow, and the other plot is obviously the experimental black body spectrum. As easily you can find this out that the Wein's distribution law is only matching with that of the experimental data in the region where the wavelength value is very small. And hence, among all the options which are given to us, we can choose the option C as our correct option, which is low wavelength, right? Moving forward with a similar question. For blackbody radiation spectrum, Rayleigh-Jeans law is correct only in low frequency or high frequency, low wavelength or all wavelengths. Once again, let us take the help of a graph. As you all can see that the continuous plot is the experimental data, whereas the dotted line shows the Rayleigh-Jeans law. And as you can see, the Rayleigh-Jeans law is matching with that of the experimental data only in the higher wavelength region to a certain extent. So, among all the options given to us, this time our correct option will be the option B, high wavelength. Now let's see. Planck's radiation law can account for energy distribution of the blackbody radiation spectrum in the low frequency region or high wavelength region or low wavelength region or entire wavelength regions. Now I think this is a very easy question, because we all know that Planck's radiation law is actually a universal law, which means it can very easily or rather correctly describe the blackbody spectrum in the entire range of wavelengths. And hence we will choose our option D as the correct option, entire wavelength region, correct? Now, a blackbody radiator does not absorb thermal radiation, is a perfectly reflecting surface, emits radiation only in the visible light region, or none of the above. Now just think that a black body does absorb thermal radiation, which means option A cannot be the right one. Similarly, a black body does not reflect radiation. If it was reflecting, then in the beginning only we would be able to see it, which means it would not be called as the black body, correct? So option B is also incorrect. As well as it does emit well beyond the visible range. It emits infrared, it emits ultraviolet, it also emits in the almost entire spectral region. So option C is also not correct, and hence we are left with the last option as our correct answer, which is none of the above. So a black body radiator does not follow either A, B or C, and hence correct option is D. What is the next question? Which of the following graphs most accurately represents the spectrum of black body radiation? Let us see what are the options given to us. Carefully look into all these graphs. Reminding all of you that whenever you think about the black body spectrum, remember that energy initially increases with the increase in the wavelength, reaches a peak or a maxima, and then declines. So, if you see the option number C and option number D, both of them do not show this kind of a variation, which means option C and D cannot be our correct answers. Now, let us look carefully the option A and the option B. We also know about a fact that with the increase in temperature, the peak of this energy graph should shift to the left, and also the area under the graph should increase with the increase in temperature of the black body. Which means the option A, which is showing that the maximum energy has been reached with the minimum temperature 1215 Kelvin, cannot be the right answer. That gives us our correct option, which is the option number B. Moving forward, this is a numerical problem, students. An electric bulb emits 2000 watt of thermal radiation. Assuming the coil of the bulb emits like a black body, emissivity is 0.3, surface area is 0.03 meter square, and the Stefan's constant sigma is 6 into 10 to the power minus 8 watt per meter square or Kelvin to the power 4. The temperature of the coil will be, we have been given 4 different options. So how can we solve this? Remember children that the problem is an application of Stefan-Boltzmann law, and all this discussion has to be done in terms of the Kelvin scale of temperature, and hence when we put in the values, namely energy per unit area, which is equal to epsilon, the emissivity, multiplied by sigma into T to the power 4. When we are putting all these values as per the given question, we are getting the value 1387. And since I have already told you that the temperature must be taken in Kelvin, our correct answer is 1387 Kelvin, which is the option A over here. Alright, so even if the option B is having the same numeral 1387, do not get confused. Directly you can strike off the answer with degrees Celsius in this problem. Okay, so let's move forward. Taking sun's temperature as 5902 Kelvin, what will be the wavelength corresponding to maximum emission from sun? Consider constant C is equal to 0.2892 meter Kelvin. Now students, once again see there is a question where we have mentioned about the sun's temperature as well as wavelength corresponding to maximum emission. Let us have this in our minds. Let us see the options. There are 4 options which are given to us as usual. Now since we have already seen that there is temperature as well as wavelength corresponding to maximum emission mentioned in the question, we can readily say that we are going to apply the Wein's displacement law, which is lambda mt is equal to constant. Now lambda m is in meters, temperature T is in Kelvin, which gives us that the constant C is in meter Kelvin. Do not confuse seeing mk as millikelvin. Alright. So as you all can see, when we put in the values of C and the temperature T, we can readily get the value of the desired wavelength. That comes out to be 4900 into 10 to the power minus 10 meters. And since 10 to the power minus 10 meter is angstrom, we can choose the correct option as 4900 angstrom. See, even if option A is also having the same numeral 4900, since it has been given in nanometers, which is 10 to the power minus 9 meter, it cannot be our correct option. So, with these kind of small little clues, you can always choose the correct option. Moving forward, which experiment is credited with establishing that photon carries momentum? Compton effect, Blackbody radiation, photoelectric effect, or Millikan's-Oil experiment? Now, students, remember that Blackbody radiation actually had established that energy acts like a particle, right? It is quantized. On the other hand, photoelectric effect had proved that light was acting like particles. And Millikan's-Oil experiment actually proved that, calculated the charge on an electron. Which leaves us with the fourth option, which is the Compton effect. Reminding all of you, when we calculate the Compton shift, we can only do the calculation assuming that it is an inelastic collision between the incoming photon and the electron within the target. So, momentum is attributed to the photon in this case, and the value of which is h nu by c, when nu is the frequency of the photon. So, with all these facts in our minds, we can now choose the option A as our correct option, which means the experiment which established that photon carries momentum was actually the Compton effect. Okay? Moving forward, Compton shift depends on which of the following? Options. Option A, incident radiation, nature of scattering substance, angle of scattering, or amplitude of frequency. Now students, from the theory of Compton effect, we know that the change in wavelength delta lambda is equal to h by m0c 1 minus cos theta. Looking into the formula, you can see that this equation does not have anything to do with the incident radiation or the nature of the scattering substance or the amplitude of frequency. It only depends on the angle theta, which is the angle of scattering, which means the correct option in this case is the C, angle of scattering. Correct? Moving forward, the energy of the scattered photon in Compton effect is it less than the energy of the incident photon, more than the energy of the incident photon, equal to the energy of the incident photon, or infinite? Now students, I hope all of you remember that we know that incident photon in case of Compton effect gives away a part of its energy to the electron with which it is colliding. So if it has given out some of its energy, obviously its energy must have gone down. So the scattered photon must have less energy than the incident one. That leaves us with the correct option as A, which is less than the energy of the incident photon. Let's move forward. The Compton shift delta lambda is equal to Compton wavelength when the angle of scattering is theta is equal to 0, 90 degrees, 180 degrees or 45 degrees. Once again, we will just consider the formula for Compton shift delta lambda is equal to h by m0c 1 minus cos theta. Over here, we know that h by m0c part is called the Compton wavelength. So, in the right hand side, if I need to have only h by m0c, this quantity within the bracket 1 minus cos theta must be 1, which means cos theta has to be 0, and to fulfill this condition, we must have theta is equal to 90 degrees. So, we will choose the correct option as our option B given here, which is theta is equal to 90 degrees. Correct? What is our next question? Compton shift delta lambda is more for, is it heavy elements, light elements? For both light and heavy elements, none of these. We know from the theory of Compton effect that delta lambda or the Compton shift is given by h by m0c 1 minus cos theta. Over here, there is no contribution from the target element, be it heavy or light or whatever. So, options A, B and C cannot be correct. Eliminating all these three, we are left with the option number 4, which is none of these. Alright? For scattering angle theta is equal to 180 degrees, Compton shift becomes, we have been given 4 different options. Now let us put the value of theta is equal to 180 degree in our known formula. When we put cos theta as cos 180 degrees, we get the value as minus 1. So 1 minus minus 1 becomes 2, and hence we are left in the right hand side with twice of h by m0c, and this option is nothing but the option number A. So for scattering angle 180 degrees, Compton shift is twice the Compton wavelength h by m0c. Compton wavelength is large for heavy elements, small for light elements, independent of elements, depends on the frequency of the incident photon. Now, as we have already discussed, what is the value of the Compton wavelength? It is h by m0c. H, m0 and c, all of these are constant quantities. So, they do not depend on the element. In this scenario, we can readily choose the option number C as our correct option, independent of elements. Alright. Let us see the next question. In a Compton scattering experiment, the incident radiation has lambda is equal to 1.372 angstroms. The wavelength of scattered radiation at an angle of 30 is, we have been given 4 different options. So this is basically a numerical problem. So what are we doing? We will remember that from the theory of Compton effect, we know that Compton shift is equal to h by m0c 1 minus cos theta. In this scenario, the wavelength lambda has been given to us. Also, the angle of scattering is given, which is 30 degrees. So what we can do is, we can put in the value of theta is equal to 30 degrees and we can calculate the value of the scattered radiation. Putting in all the values, as you can see I have shown over here, we get the value as 1.375 angstroms. So we can choose the option C as our correct option. Alright. X-rays with wavelength lambda is equal to 1 angstrom are scattered from a carbon block. The scattered radiation is viewed at 90 degrees to incident wave. Ke, which means kinetic energy imparted to the recoil electron, is 4 options are coming for us. Now students, remember that what will be the value of the kinetic energy imparted to the electron? It will be exactly equal to the amount of energy which has been lost by the incident photon. That is, the incident photon comes with some energy, collides with the electron, gives some of its energy to the electron, and in turn, its energy gets decreased. But where does this energy go? This energy actually goes to the electron, and the electron recoils. So basically, the kinetic energy in this case is nothing but the energy difference between the incoming photon and the recoiling or the scattered photon. So as you can see, the kinetic energy is hc by lambda minus hc by lambda prime, where lambda is the incident wavelength and lambda prime is the scattered wavelength. Moreover, it has been given in the problem that the scattered radiation is viewed at 90 degrees, which means the scattering angle is 90 degrees. So first what we will do, first we will calculate the scattered wavelength lambda prime by putting in the formula. As you can see in this scenario, lambda is known to us, h by m0c, these are all constants. So we are going to put the value of cos 90 and we will calculate the scattered wavelength, which comes out to be 1.0237 angstroms. By taking this value as lambda prime, when we put it into the formula of kinetic energy, we will get the value of energy in joules. Remember, we are using hc by lambda. See, h, the unit of h or Planck's constant is joule second. C is meter per second and wavelength is meters. So the second cancel, meter cancel. So the unit of energy that we are actually going to get is joules, the value of which is 0.471 into 10 to the power minus 16 joules. But all the options that we can see over here, 3 of the options are in electron volts, whereas one option is in joule. And the joule value is not at all closer to what we have got. which means we'll have to convert this energy that we have calculated in joules to electron volts. Always remember that 1 joule is equal to 6.242 into 10 to the power 18 electron volts. You can always remember this value as well. So, when we put in this conversion, we get that the kinetic energy is coming out to be 293.97 electron volts, which is very approximately or very close to 294 electron volts. Which means after so many steps, we can derive or we can get to the final option, which is option number C, 294 electron volts. Correct? So, that is all in this video. Do keep watching the next videos of this series, where not only quantum mechanics but all the other topics would also be covered in the form of multiple choice questions. So, that is all for today. I'll see you in the next video. And once again, do not forget to like, comment and share. And also, do subscribe to the channel. I'll see you in the next video. Bye-bye. See you all soon.